Honors Chemistry. This is the answers video for Lesson 18, Solutions, really Solution Stoichiometry. For period 1, it was assigned on Monday. For period 3, it was assigned on Tuesday, and it's due 1 week later. It's a fairly long assignment. It's really 2 assignments rolled into one. So let's go ahead and get started on this. So the purpose of this, I'm going to do all of these with you, but I want you to try to do them on your own. It's just to be sure you know how to recognize different ways that these relations can be written. So I gave them these names. These are just names I made up. The expanded form, which is a way of writing grams to liters or moles to grams, showing that relationship. And it's the way you've been seeing it. So let's start with number 2, because you've seen this one many times before. 1 mole of H2O equals 18.02 grams of H2O. But the way you might see this written in a question is like this. So this is what I want you to write out. Now this is the short form. It may seem not short because I'm writing it as a sentence, but the way that I eventually write this relationship is short. Okay, so the molar mass of H2O is 18.02 grams per mole. This 18.02 grams per mole, this part, means exactly this. So if you see this in a question, you know that you can convert it into this because you know how to work with this. It becomes a ratio, either this over this or this over this, depending on what you need in that particular question to cancel, for the units to cancel properly. Alright, so that's kind of all I'm looking for you to do here. So in this one, I want you to just write this, that this would be grams per liter, so that's going to be a density. And notice that I'm using carbon as an example. 9.32 grams of carbon is not a, this is not a permanent or a regular density. It just happens to be for a problem that I'm making up here. For example, 18.02 grams per mole of H2O is always true. That's always 18.02 grams per mole for the molar mass. But density is whatever the problem says it is. So I'm just making up a number here, okay? So, but the way this would appear in the problem is the density. Okay, so the density of carbon is 9.32 grams per liter. Again, that's not a number that always appears with carbon. It's just for this particular problem it is. But if you see this, that means you can write it like that. And what it means is grams of carbon, if you were to actually write it, grams of carbon. They don't write this way in the problem, but it's grams of carbon per liters of solution. So that normally would not be written in the problem. But you have to understand that that's what that means. Okay, density is always per liters of solution. Okay, what about this one? What would this one be? So now I'm asking you to go in the other direction. The molar mass of CO2 is this, so you could write this. You've seen this one a lot of times before, right? Okay, so that's the expanded form, and that's the way you're used to seeing it. So now you can turn that into a ratio in your stoichiometry problem. Okay, how about this one? Okay, so again, density is grams of the solute, that's CO2, it's what's being dissolved, in liters of solution. That's what that means. So grams of solute, liters of solution, even though you don't see solute, the CO2 there, and solution there. But this is how you would do that. So again, you can make a ratio out of that. So I want you to recognize how you would see this appear in a question and how you would convert it. Okay, and we're going to do this a few times in this lesson. Let's just finish these up. So molar mass CO2, okay. We did this one already, all right? Somebody pointed out those were the same. You don't have to do it again. I think I told you to do it again, but don't do it again. Okay. Molar mass of helium, there you go. Okay, so you did it again, good for you. So this is the way you're used to writing a molar mass, but this is the way a question might state it. Okay, here again, you got liters and grams. That's going to be a density, grams per liter. Okay, so this one is going to be, oh, whoops, I'm supposed to do it the other way. Sorry, that's already the expanded form, so let's go back. So we're going to write it in the short form. If it's given to you in expanded, then you do it in the short form. Okay, so the density, okay, that's the way you'd see it written in a problem. And you convert it to this. Okay, what about this? Okay, so this one, it's in the short form, so we're going to convert it to the expanded form. So it doesn't tell you what the gas is, so you can just write gas. And it can be in a solution. Carbon dioxide mixed with water to make carbonated soft drinks is gas in a solution of water. So that can happen. Okay, so that's how you would write that. Okay. Again, once you see some examples and problems and I have a chance to point them out to you, this will make more sense as to what we're doing, why we're doing this. Okay, let's go ahead and do some problems. We did the first two in class, or these two at least, 9 and 10. Okay, so I'm going to go ahead and do these. Okay, so what is the molarity of 2.3 moles of potassium hydroxide in 250 milliliters of solution? Okay, so you're given two numbers. Normally we were always given one number, and then what are we looking for? Well, what we're looking for here is what is the molarity. So molarity, whenever you see that, you want to convert it immediately into moles of solute. Your solute here is KOH. That's what's getting dissolved in water. It doesn't say water, but again, if it doesn't say, you always assume it's water, because that's virtually the only solvent we're going to be dealing with. So moles of KOH per liter of solution. That's the KOH and the water mixed together. We just call it solution. It's everything mixed together. So now that we have this, we need to deal with the numbers that go over on the right. And this is what makes this unusual, you'll notice, is now we have two units of measure we're solving for, moles and liters. Before it was always just moles or grams or liters. It was one unit of measure, but now you got two. You also have two starting units here. Okay, so you notice that you have moles on the top, liters on the bottom. So what we're going to do is, what we're starting with, we're going to set up in kind of that same way. So it's going to be 2.3 moles of KOH per, here's what it's saying. You have 2.3 moles of KOH in 250 milliliters of solution. So you have this many moles of KOH for every 250 milliliters of the solution. Okay, so the way you solve these problems is you first just deal with the numerator first. You could deal with the denominator first if you want, but let's just start with the numerator. You deal with one at a time. So on the top, we start with moles of KOH, and in our final answer we need moles of KOH. So since those two are the same, you don't need to do anything to the top. It's already in the units of measure that you want for your final answer. So you don't need to do anything up top. So now we go down to the bottom, the denominator. You have milliliters of solution, you need to end up with liters of solution. So the this conversion you should just have memorized. It's 1 liter equals 1,000 milliliters. Okay, that's true of any substance. A liter equals 1,000 milliliters. Always, no matter what the substance is. But you always want to put a unit of measure along with the substance. So we're going to write solution and solution. Why? Because that's what we started off here, is milliliters of solution. And that's what we're trying to resolve, is trying to get these two to match up. So it's liters of solution, milliliters. So which one goes on top, which one goes on bottom? One goes on top, one goes on bottom. You need milliliters of solution to cancel out, and it's on the bottom here, so you need to put it up on the top in your conversion. So it's 1,000 milliliters of solution. And since you need liters to end up on the bottom in your final answer, that means the 1 liter solution has to go on the bottom. Okay, so milliliters of solution have canceled. The only unit you have left on the bottom is liters of solution. You already had moles of KOH on the top, so everything's ready. So 2.3 times 1,000 divided by 250, and that's going to equal 9.2 moles of KOH per liters of solution. And the way you should really write that is, that's molarity, so it's 9.2 with a capital M after that. You don't have to write KOH or solution or anything, it's just capital M. And that's said to be molar. That's the way you read that, 9.2 molar. It means it's the molarity of the solution, 9.2 molar. Okay, so this is good. This is also a good answer right there. Okay, all right. Okay, let's go on to the next one. This one's going to be a little trickier. Okay, so how many moles of HCl are there in 350 milliliters of 1.7 molar aqueous solution? Aqueous solution just means it's mixed with water, and as I've said 100 times already, we're always going to assume that something is mixed with water, but still you say aqueous solution, that just confirms it's mixed with water. So what are we looking for? The first few words here, how many moles of HCl? So we come over here and we have moles. HCl is hydrochloric acid. Sometimes I write that as a capital L, even though it should be lowercase. Because some students think it's a 1 or an I or something, but it's HCl, hydrochloric acid. It really should be lowercase l. Okay. Now, what are we starting with? Well, this one's a little tougher than the one above. You got 357 milliliters, but you also have 1.7 molar. And remember, molar is 2 levels. It's moles per liter. So you already have 2 levels there. So I'm going to bring this one over here, and I'm going to start with 1.7 molar, but here's how I'm going to write it. 1.7 molar means 1.7 moles of the solute. This is what's being dissolved in the water, it's the hydrochloric acid. So 1.7 moles of HCl for every 1 liter. You don't have to write the 1, but I like to, of solution. It's moles of solute over liters of solution. Okay? All right. Now, what do we got to do? We need to finish with moles of HCl on the top, and we already have moles of HCl here. So we don't need to do anything to the numerator. Moles of HCl, it's good. But a funny thing happens here. In the denominator, you have 1 liter solution, and over here, you have nothing in the denominator. So this has to disappear. Okay, well, we only have one number to work with to make this disappear, and that's the 357 milliliters. So sometimes these problems are quite honestly just like little puzzles where you're trying to figure out how to play with the units to get them to cancel out right. And once you get the units to cancel out, then you know you have your numbers set up properly. So if we're dealing with liters here and milliliters here, we know we're going to need this somewhere along the way. That relationship. So let's go ahead and convert liters to milliliters. So what we're going to do is, and it's of solution, so it's times 1 liter of solution for every 1,000 milliliters of solution. Okay, so liters of solution cancels with liters of solution. Good. So now down on the bottom we have milliliters of solution, but the problem is we need to end up with nothing on the bottom. You don't have any denominator there. So how do we make this cancel out? Well, that's where this number comes in. And again, that may not have been obvious to you. I gotta tell you, when I first started doing these, that wouldn't have been obvious to me. But you just kind of play with the units until you get them like puzzle pieces to fit together where everything works well. Okay, so I'm going to put that 357 up on top. You don't always have to have a ratio, a fraction, numerator, denominator. In this case, you just have a top, 357 milliliters, and it says how many moles of HCl are there in 357 milliliters of 1.7 molar aqueous solution. So the 357 milliliters is of solution. That's what it's saying there. I didn't seem to give myself enough space here, so I'll do the best I can. So milliliters of solution cancels there and there. So now you no longer have any units on the bottom. These both canceled out, nothing over here. So now you're ready to run the numbers. 1.7 times 1 times 357 divided by 1 divided by 1,000. Let's go ahead and do that. And that gives us 0.61. And that's good to the 2 significant figures. So that's how many moles of HCl you would end up with. So kind of stop. You don't have to rush through these. I know there's a lot of them, but you have a week. Think about this problem. Think about how you set it up. How did it work out, okay? How did I know I should put 1.7 moles per liter here instead of the 357? Because I had both of these numbers to work with. The answer is you just kind of learn that a volume is probably going to cancel out somewhere in the middle of the problem like that. And it's just the experience of solving these problems. Okay? All right, let's keep going. I'm going to solve the vast majority of these problems for you. I really want you to see examples, but again, if you're serious about learning the subject, you got to try them on your own. So try this on your own before I do it, okay? So pause the video, see if you can set it up. Okay, so here we go. So it's asking again, what is molarity? Okay, so that means we need moles over liters, and it's moles of solute, and in this case the solute is NaCl, sodium chloride. And the solution, as usual, is going to be water. Okay, so over liters of, excuse me, not water, it's liters of solution. It's the NaCl and the water mixed together, so it's solution. That's the definition of molarity. Moles of solute over liters of solution. Okay, so there we go right there. Okay, so what are we starting with here? Well, we have 5.4 grams of NaCl. That's just going to be a single unit of measure. It's not like molarity where it's 2 levels like the last problem. And there's liters. That's 1 level. And you can see that grams over liters is eventually going to lead us to moles over liters, okay? So you kind of start to recognize these patterns. So I'm going to come over here and put the 5.4 grams of NaCl over 0.24 liters of, and that should be solution, okay? Because if it's not solution, then it doesn't work. It's not of the solvent. That's the solvent. The solution. It's those two mixed together. So that's one of the reasons it's good to watch these videos, because I'll correct mistakes like that. Okay, so it's liters of solution. Okay, all right, so we got the top. We do top first. Again, you can do bottom first if you want. Why don't we do bottom first this time? Here's why. You got liters of solution here and liters of solution here, so you don't have anything to do on the bottom. It's already in the correct units of measure. So now we go to the top, and it's grams of NaCl to moles of NaCl. Well, you've done that 1,000 times. It's molar mass. So we go to the periodic table. Okay. Sodium is 22.9. Chlorine is 35.45. Let me do that a little closer up. 22.9 for sodium. Chlorine 35.45. So we're going to sum that up. I should know that one off the top of my head, but I don't. And that's 58.44. Okay? So why don't we say it the way we were doing it? The molar mass of NaCl equals 58.44 grams per mole. Okay, so that's the way you would see it in a problem a lot of times if they gave it to you. But the way we want to write it for our conversion, let's write it down here, is 1 mole. Okay, so now we got one of these is going to go on top, one of them is going to go on bottom. So which one? Again, forget about the denominators here. We're done with the denominator. So what do we need to do? Okay, I think hopefully most of you are kind of catching on, but if you're not, come to tutoring and let me work with you on this. You need this to cancel out because you need it to go away because your final answer is going to have moles of NaCl. So we're going to have 1 mole. So grams of NaCl cancels. Top and bottom like that, they cancel across. So now you have moles of NaCl, which is what's in your final answer, and down here you already had liters of solution, so you're ready to go ahead and run the numbers. So it's going to be 5.4 times 1 divided by 0.24 divided by 58.44, and that gives us 0.385, two significant figures here, so 0.39. So 0.39 moles of NaCl per liter of solution, or the final answer should really be written as 0.39 capital M, molar, 0.39 molar. Okay, all right. Keep going. Stop the video, read this problem, stop the video, think about it. How would you solve this one, number 12? So what are we looking for in this problem? What do you want to come up with in your final answer? Okay. You want to find grams of NaOH. Let's just read the whole problem. You want to create 500 milliliter solution of 1.2 molar NaOH solution. How many grams of NaOH would be required? This is actually a pretty typical AP question or college level test question, really even advanced high school level test question, because it's a lab question. Okay, you're going to go into the lab storeroom and you got to get out the NaOH. And they want you to measure out how many grams, the teacher or the whoever tells you that you need to create 500 milliliters of 1.2 molar, so that's the concentration, sodium hydroxide solution, sodium hydroxide in water. So how many grams of sodium hydroxide are you going to measure out on the scale? This is something you would measure on the scale. How many grams? How much does it weigh? So how many grams on the scale of NaOH would you need? Would you need to measure out on the scale and then mix with 500 milliliters of solution? It's actually the two mixed together are going to be 500 milliliters, and we'll talk about that sometime. I think we may have mentioned it, how you mix a solution like that. But for right now, let's focus on what we're doing here. So what we're trying to find is grams of NaOH. So way over here, I've got grams of NaOH. That's what you're trying to find. That's what the question, how many grams of NaOH, the question tells you you're trying to find. Okay. Again, we're starting off with a volume and a molarity. So the molarity is really our main number here that we're working with. So we're going to come over here and write that as 1.2 moles of solute. And the solute in this case, whatever this is the smallest amount, it's the lemonade in other words, but you don't want to drink this stuff, trust me. But that's what you're mixing. It's the powder. NaOH comes in these flaky crystals in a container. And it's over liters of solution. Okay, but in this case, it's 500 milliliters. Excuse me, I take that back. I did that wrong. It's per liter of solution. It's molar, so it's per 1 liter of solution. We're going to use the 500 milliliters here in just a second. Okay, sorry, I slipped up on that. Okay, so that's what molarity means. It means 1.2 moles of this over 1 liter of solution. Okay, so let's look at the top. We need to go from moles of NaOH to grams of NaOH. So right away, hopefully you're getting to recognize that's a molar mass conversion. Grams is the mass, moles is the moles, molar mass. You're going from moles to mass. Then you see you have something in the denominator here, a liter of solution, and you don't have anything in the denominator here. So that's just like problem number 10. All right? So let's do the top first. We need the molar mass of sodium hydroxide. So sodium is 22.99, and then hydrogen, one hydrogen is 1.01, and oxygen over here is 16. You add all that up and you get exactly 40. Okay, so 1 mole and you can write that to two significant figures. It becomes exactly 40 grams of NaOH. Okay, so there's your conversion. Okay, so we're dealing only with the top. Forget about liters of solution for right now. Okay, so which one of these goes on top? Which one goes on bottom? You need moles to cancel out. You need this one to cancel out. Moles NaOH is gone. Now you have grams NaOH on the only thing left, and that's what you want for your final unit. The next step is we need to make liters of solution cancel. Okay, so I didn't leave myself enough space here. Let me just erase it for right. Put it way over here. Okay, there it is. Okay, so what do we do? Well, we got liters here, we got milliliters here. So what we need to do is get liters converted into milliliters without changing the value at all. So we're going to use our 1 liter equals 1,000 milliliters, and we're dealing specifically with solution, so we're going to write it like this. We need liters to be on top, so it'll cancel with this. 1 liter of solution over 1,000 milliliters of solution. Okay, so liters of solution cancels with liters of solution. And all we have on the bottom is 1,000 milliliters. We have milliliters of solution on the bottom. but we don't have anything on the bottom here, so that has to somehow cancel out. What do we use to cancel that? This guy right here, 500 milliliters. You just put that up on the top. There is no bottom to that. So 500 milliliters, and again, it's of solution. So milliliters of solution, milliliters of solution. So we no longer have any units on the bottom, on the denominator. They're gone, so there's nothing there. And the only units on top we already did was grams of NaOH. So now it's going to be 1.2 times 40 times 1 times 500 divided by 1 divided by 1 divided by 1,000. And that gives us exactly 24. The two significant figures, so I'm going to leave it at that. I didn't leave myself a lot of space here, so I'm going to write it down here. So it's 24 grams of NaOH. So that's how much you have to weigh out on your scale, and then mix in to make 500 milliliters of solution in order to have a 1.2 molar solution. You need that many grams of NaOH. Okay, so remember, grams is in our world. That's something that we can measure. All right, so there it is. Okay, that one was a little longer. I should have started, like I always tell you, start way over here so you don't run out of space. I ran out of space. Okay, so go ahead and watch that one a second time if that's still a little confusing. And every time you watch it, and actually every time you write it out yourself, even though that's time consuming to do, you'll get that much closer to understanding it. Okay, let's keep going. Okay, 13. Again, try it on your own. Actually, I'm going to leave this one for you to do. It's exactly the same as 12. It says you want to create 347 milliliters of a 2.3 molar NH3. That's ammonia. How many grams of NH3 would be required? It's done exactly like this one. It's just the numbers and the substance is different. The only thing substance matters is the molar mass is going to be different than it was for sodium hydroxide. Other than that, the problems work exactly the same. So I want you to do 13 on your own, okay? And that's one that I'll check. Done exactly like 12. Okay, let's go down here now. Okay, what is the molality? So now we're dealing with a molality question. Of 3.7 moles of LiOH, lithium hydroxide, in 0.89 kilograms of water. So this time I did mean to say water. Why? Because it's molality. So what is molality? It's moles, let's just write it generally. It's moles of solute over kilograms of solvent. Solvent is not the solution. Solvent is just the water itself. The water and the lithium hydroxide together are the solution, but the formula for molality is moles of solute over kilograms of solvent. And that's what we're given here, is kilograms of solvent. Water is the solvent. It's what's doing the dissolving, okay? So it's what is the molality? So let's go ahead and write it here. So it's moles of LiOH, that's the solute, over kilograms. And you can just go ahead and write H2O. If you want to write solvent, you can. Okay, and so we're trying to find that, okay? Okay, so what are we going to start with? Well, you're just going to start with these. You got moles, kilograms. Moles, kilograms. So you're just going to put this on top of that. So this is really a pretty straightforward problem. There's no conversions involved, in other words, okay? So it's 3.7 moles of LiOH over 0.89 kilograms of H2O, which is our solvent. Okay, so we already have the units. We don't need to make any conversions. We just have to do the math here. So 3.7 divided by 0.89, and that's going to give you 4.16, but we can only have two significant figures anyway, so call it 4.2. And that's all there is to that problem. Okay. All right, what is the mass percent? So let's just knock these down together. And you should be trying all of these on your own first. Okay, that's the deal. Otherwise, you're not going to get any better at it. And the next thing you know, you're doing some really hard problems where you have to do this stuff and you're not good at it. Do it. Okay, so mass percent, let's just write over here what it is. It's grams of solute, particularly of the solute you're interested in. There may be more than one, but in these problems I'm just giving you one. And then it's over grams of solution, that's the solute plus the solvent together, the total mass of the entire solution in grams, in other words, times 100%. Okay. All right, so what do we do? Well, we're given grams of the solute, SR, that's strontium oxide, and we're given the grams of the solution. So we're given this is the grams of solute, is this, and grams of solutions down here, so we're just simply going to write this. 8.0 grams of solute over 45.2 grams of the entire solution together. So that's the definition times 100%. That's the definition of mass percent. So this divided by this. So 8 divided by 45.2 equals 0.176. Now I'm going to multiply that by 100. And I get 17.69. Two significant figures right there, so we'll just call it 18%. So of this solution, the entire solution is 45.2 grams. Of that, the strontium oxide is 18% of the total solution. That means the water, if that's the only solute there, the water would be 100% minus 18% would be 82%. So the water would be 82%. It didn't ask you that, but I'll go ahead and write that here, just so you understand the concept. 18% is this, 82% is the water that it's dissolved. Okay, keep going. Mole fraction, very similar to mass percent, except you're dealing in moles, and you don't multiply by 100%. Okay, so I made this one a little more complicated. If I'd given you moles and moles here, it would have been an easy problem. But I didn't. I gave you in grams. So now you're going to have to convert this to moles, okay? And you're going to have to convert the water to moles. So we're going to need to use this whole space here. I'm just going to tell you that. So let's start with the molar masses down here. 1 mole of KCl, potassium chloride, equals, okay, we got to go to our periodic table. So potassium 39.1, chlorine 35.45. And that gives us 74.55 grams. Okay, let's do it now for water, and water we already know, right? So water is 1 mole. If you don't, go figure it out. 18.02 grams of H2O. Okay, so those are our molar masses. Now we need to convert each of these into moles. So KCl into moles, and then we got to convert water into moles. So let's do KCl first. So we're going to start, we've got to use our space wisely here. So KCl, let me write that actually, 25. And I'm using every bit of space that I have here. 25.2 grams of KCl times 1 mole KCl. I'm just using this down here, and we need grams on the bottom, so 74.55. So grams of KCl, so that's going to equal, that'll tell us how many moles of it we have. And that's going to be 0.338. Okay, now I'm coming over here and I'm going to do the water. So that's going to be 102.4. Line here. And we need moles on top, grams on bottom. Grams H2O cancels and cancels. So it's going to be 102.4 divided by 18.02, and that's going to give us 5.68 moles. Okay. I'm going to switch over to another piece of paper because I don't want to write down here. I need space for that. And I'm running out of space up here. Okay, so here we go. So you may want to do likewise, or you can do it on the back side or do it somewhere else. Okay, so mole percent, which is that letter chi, it's kind of a funny looking X, is moles of solute over moles of solution. But what is solution? Because we don't have solution here. We have solute and we have solvent. So it's the two of them added together. So it's over moles of KCl plus moles of H2O. That's the moles of solution. The two of them added together, okay? So I'll go down. So that's going to be, for KCl, it's going to be 0.338. And I'm going to tell you, all these moles are going to cancel out, so I'm not even going to write the units here. They're all going to cancel out. They're all moles. So 0.338, this down a little bit like that. 0.338 over moles of solute, which is KCl. I should have written that there. Moles of KCl over moles of KCl plus moles of H2O. So 0.338 over 0.338 plus this, 5.68 for the water. So this is the moles of the solution, everything mixed together. This is the moles just of the solute. Excuse me. So we go ahead and do the math on that. And that gives us this. And there's three significant figures. Do I have three significant figures? Yeah, it looks like I do. 3 and 3. So there's the answer. So even though it's called a mole fraction, you express it as a decimal. But there's the fraction right there, but you express the final answer as a decimal. There it is. It doesn't have any units of measure. All the moles canceled out. It's just a fraction. Okay? So there you go. That's how you do that one, number 16. Okay? All right. So take a picture of that. I'm going to move it here, and there we go. Let's do 17. So what is the parts per million, ppm, of 0.02 grams of aspartame, excuse me, in 2 kilograms of H2O? So H2O is the solvent, and this is the solute. But parts per million is grams of solute over grams of solution. The grams of solution. So you're going to have to add these two together. The only conversion you got to make, the switch you got to make is this. You got to turn this into grams. A kilogram, so you should know that conversion. 1 kilogram equals 1,000 grams of anything. Okay, so let's go ahead and make that conversion first. Okay, so you have 2 kilograms of H2O times, okay, you need kilograms on the bottom to cancel with that. 1 kilogram H2O over 1,000 grams of H2O. Okay, kilograms cancels with kilograms. You have 2 times 1,000 divided by 1 is 2,000. So that equals 2,000 grams of H2O. Okay, and again, parts per million is going to be grams of solute over grams of solution times 1 million. Okay? Get rid of that. Okay, so let's go ahead and do that. Grams of solute is 0.02, very small amount. So I'm going to try to kind of record this so it doesn't get messy here. 0.2 grams of AS. I said acetane, that's actually arsenic. And that can be in your drinking water, but as long as it's not a high solution, it's okay. Okay, then you have the solution is this, the solute, plus this, the solvent. Okay, so when I take 0.2 plus 2,000, okay, I divide 0.2 up here, divided by 2,000.2. That's really what that's going to be at the bottom. Let's see what that comes out to be. It's a very small number. Divided by 2,000.2 is going to give us this. And since I'm going way past my sig figs here, it's 999. I'm just gonna call it 1 at that point. And that's only one significant figure there, okay? But you only have one significant figure there, so I'm just gonna stop there. Now, you're not done though. That times 1 million. See, that's why you use this for very small concentrations, because you don't want to be dealing with numbers like that. That would, a percentage would be a tiny number. So we're gonna multiply that times 1 million. And we get 99.9, and to one significant figure, that's actually 100. And it's a part per million. It's not a percent. It's not grams. There's no unit of measure. So the parts per million are 100. It's just parts per million. So for every million molecules of this solution, 100 of those are arsenic atoms. Okay? That's not very much. That probably won't kill you. I don't know. That might be a little high for arsenic. I don't like that many, okay? Even in a million molecules of solution. What that means is out of a million molecules or particles of solution, 100 are arsenic. That means a million minus 100, which would be 999,900 would be water molecules, okay? A million minus 100. Okay, so there's your final answer. Okay, this video is going a little long. I'm going to wrap it up here. That'll keep you busy for a couple days. This is a 1-week assignment. I'll put up some of the other answers later on. Maybe not tonight, but you have this to get you started, okay? Again, be sure you know how to do them. Don't just copy the answers. Be sure you understand them. Even do some of them a second time to be sure that you really understand the concept. Okay? So that's it. I'll see you in class.